Hello again. It's the month of October. Halloween's coming up, so I thought I'd do something that fear, uncertainty, and doubt, or FUD, is injected. We're going to talk about asteroids coming in from out of the sun, not from the sun, just in the direction of the sun. So, in previous presentations, I talked about not being able to observe, see, or detect certain things like asteroids, and if they're too far away, too small, too dim. Maybe even professional observatories can't see them. If they're not bright, if they're not reflective, they're too dim to be seen. Maybe we can spot them in infrared or radar radio frequency, but you have to know where they are to see them, to point at them. Then there's another category, which is they may be there. They may typically be reflective, bright enough to see, but if they're coming from the direction of the sun, you won't be able to see them because you'll be blinded by the sun. So that's the ones we're going to be paying attention to. So there is multiple classes of asteroids. This particular class is called Atiras or Apheles, and they're part of the interior Earth objects asteroids. These are asteroids that circle the sun, just like the Earth circles the sun, and their orbit is within the orbit of the Earth around the sun. So they're circling the sun, we're circling the sun, and we would have to look in the direction of the sun in order to see these circling the sun. Not all orbits are circular. Some orbits are more deeply elliptical, and they could come closer to the Earth or farther away. But how you would spot these is you would have to wait until this object in its orbit around the sun, where the sun's reflecting off of it, is at greatest eastern or western elongation. That's the basically the distance from the sun as seen from the Earth, and that object is farthest away from the sun. But the most you'll ever see is half of it, because the sun is illuminating one half of it, and from Earth we only get to see the half that's illuminated. The other half not illuminated is dark. And even worse, if the object is directly between the Earth and the sun, it's kind of like a new moon. The sun is illuminating the backside of it, and the side that we can see, there is no illumination. So it's like a new moon versus a full moon. So the best way we could see these is at greatest elongation, east or west. The percentage of illumination changes. If you've ever looked at what they refer to as an inferior planet, meaning it's a planet whose orbit is inside the orbit of the Earth, meaning Venus or Mercury, then you'll never see a full Venus or a full Mercury, because that would say the sun is illuminating the backside of it. So you always get to see like a crescent one way or the other, or a half. And that's about as much as you're going to see illuminated of it. So think of these asteroids as the same sort of thing. You'll never get to see more than half of it illuminated. So the latest one was found on September 27th of 2025. Yet we found another one, and recently. So, we should not make the presumption that we found all of them, or we know the size of them, or how far away from the Earth they are in their orbit. So we have no full assessment of the Earth threat potential of them. This one was found so recently that it doesn't have a mythological name. It's just 2025 SC79. The C stands for candidate, and 79 is the 79th one in the list. In 2025, we have 79 solar system candidates. So we still have to find out more details about it. But you can see there's the Earth off on the right, and there's Mercury and Venus, and the sun in the center, and this thing has an elliptical orbit, and those little vertical lines that you see are an indication that the orbit of this asteroid is tilted. It's not tilted this way, it's tilted this way. Space is three-dimensional. How can these orbits change once this thing is in orbit around the sun? And there are three things that can affect it. There's radiation reflection pressure. There's the Yarkovsky effect. Many people might not have heard of that one. And there's gravitational slingshots, which you might have heard of those. When this thing is going around the sun is bathing it always on one side. It may actually rotate, so it may be distributing heat evenly. As that heat bounces off that object it's going to push on it. That's the radiation reflection pressure. And as one side of it gets heated, if it rotates, the heat is going to be radiating off of it, which causes a rotational push. This causes it to spin along a vector in one direction or the other, depending upon its rotation. That's the Yarkovsky effect, and it's due to solar heating and radiating of the heat. And then if one of these objects gets close to Mercury or Venus, the gravity of Mercury or Venus, which are planets, can actually bend its orbit. And the best example of something like that is Voyager 1 and Voyager 2 purposefully did flybys from Earth to the various planets in the outer solar system as bends by the gravity so that it could change its course and accelerate. So you have three effects that can change the orbital path of one of these things once it's been established. There are currently no known on a course for Earth Atira asteroids. Things can change over time. So where would we be best positioned to observe these? We've already talked about elongations, but that then proposes that could we get a better spot to look from? Well, Lagrangian points, the 5 Lagrangian points. L1 doesn't really solve a problem because from the Earth's perspective, that's still staring towards the sun. L2 would be behind the Earth, behind the moon, and that's further away. And the Earth and the sun and the moon are all still in the same direction, so not good. L3 is on the opposite side of the sun from where the Earth is. So even though it would be able to observe this, how would it communicate back with, how would the space probe communicate back with the Earth? Because the sun's in the way. So the best place to put a deep space probe that would stay in orbit is either at L4 or L5. What we know about L4 and L5 is they're not fixed. They actually slide forward and backward, depending upon kind of a gravitational sloshing effect. So even if we put something at L4 or L5, it would need fuel to maintain its orbital position in its orbit around the sun. So will we look at it in light? No. Will we look at it in infrared? No, because you're still staring towards the sun. We should look at it in high frequency, high gigahertz radio. The sun does not produce radio at all wavelengths. There are some gaps. As you get up towards the higher frequencies, the highest we've observed the sun at is 26 gigahertz. So what you would want to do is produce a radar beam output at the 30 gigahertz or higher level and just aim it in the general direction off angle from the sun. So from, what you would think of as an elongation all the way towards the sun, just bathe that area, sweeping it with a radar beam, and anything that bounces back is going to be one of these asteroids or Mercury or Venus. So you have to wait until they're not in the way, but they go around the sun pretty quickly. You'd need a large receiving antenna or an array of these satellites, and they would effectively be one astronomical unit about 93 million miles away from the sun. So need a big array or multiple antennas. You could actually create a radar observing capability that could spot these even with the sun in the way, because the sun wouldn't be putting out a signal at the same frequency that you're using for your radar. So the sun would just be essentially a black spot on your radar. No, nothing, the signal goes into the sun, nothing comes back out. So there's how you can spot them. A radar satellite at L4 or L5 at roughly 30 gigahertz. And you just sweep the area, and whatever comes back has got to be from one of these things that otherwise you can't see. How many of them are there? We currently know of 30 Atira asteroids. None of them are a direct threat currently to the Earth. We know that they're not that big. They're not planet killer size things. They're not dwarf planet size. But since we haven't found all of them, we don't know what the maximum size one is. If it was one of these asteroids and it was larger than Mercury or the same size as Mercury, even if it wasn't fully illuminated, we would have spotted it now by solar reflection, unless it's very dark. It has like a charcoal surface on it and has a very low albedo. But we don't know. If we put a probe out there and we use radar, we may spot, there's a lot more of them than we thought. Kind of like it is with, until we had a program that was looking for asteroids that were on an Earth orbit crossing basis, we didn't know there were several thousand of them, most of which have no effect on the Earth, don't even actually affect the Earth's orbital path, as the Earth is not going to interact with it. It's too delayed. Until you know, you're not sure. We needed some way of finding the missing ones because we don't know how many missing there are. So let's use radar. But what about other near Earth objects? So on the right, you can see 3 different types of orbits. These are orbits of things that go around the sun. You have those that make their way all the way out to the orbit of Mars. So you can have a very elongated orbit for one of these asteroids. And part of the time it's close enough to the orbit of the Earth that maybe we should pay attention to it. Others are far enough away that they're not actually going to interact with the Earth's orbit. Then if you take that elongated orbit and you slip it slightly so that its focal point is a little more towards one side than the other for the sun, now you have an Earth crossing orbit where the orbit can extend out beyond the orbit of the Earth. And those are called Apollos. And then you have the ones where the slippage is literally crossing the axis of the Earth's orbit around the sun. And those are called Atens. Those are the ones that probably present the biggest threat to Earth. But since space is 3D, every one of these orbits is kind of like a flat disk, and it can be tilted at multiple angles. So how it interacts with the Earth's orbit around the sun vary. So in summary, not being able to observe something because you don't have the right kind of instruments, things like, once Chandra is gone, how do we see an X-ray? But then you have these things that are hard to see because they're coming at you from the sun, and you can't stare at the sun to see them. And even if you blot out the sunlight with a disk, it could be behind the disk, so you still wouldn't see it. They're out there. We know of a few of them. The total number of them, we don't know. What's the biggest one? We don't know. Which ones are threats to Earth? We don't know. But we also know that these orbits can change due to the radiation coming off the sun and gravitational slingshots by Mercury or Venus. So we need a new way, a new kind of observatory to spot these things, which, until you know whether or not they're a threat, just presume they are, because big rocks hitting the Earth is a threat. A radar satellite at roughly 30 gigahertz or higher at Lagrange Point 4 or 5 would be the best way of taking a look and spotting. And remember, these things are in close orbit around the sun. So if we did find one and it was on a path that might affect the Earth or the moon, we wouldn't have decades or years to see what's going on or to do something about it. We would have literally well less than 1 year, maybe even just days. If it's coming in from out of the sun, how do you know if it's going to affect you or not? And where this started was a Fraiser Cain YouTube video. And then what an Atira asteroid is, this particular one, what NEOs are, radiation reflection pressure, Yarkovsky effect, orbital elongations, Lagrange points, and sun radio emissions. Okay, comments, questions?
I think I take exception to something you said.
Yes.
When you were saying that anything circling the sun, if it gets between us and the sun, we wouldn't see it because it's a silhouette. That's okay.
Yeah.
But if it's going to go around the sun, as long as it's not behind the sun, we could still see it. We'd see its face, wouldn't we?
You won't see a full face of it. Remember,
okay.
Remember the only.
You're right. Yeah, you can. Yeah, because the sun
Remember, you don't always see a full moon every day.
That's right. Yeah.
Because the moon's in orbit around the Earth and the sun is at an off angle from that. So you only get to see a full moon for a couple of days every 28 days. Now that's something that's in orbit around the Earth. If the Earth is in orbit around the sun and this asteroid is also in orbit around the sun, it will exhibit the same behaviors as minor planets like Mercury and Venus. Have you ever seen a full Venus? No, because then that would mean that the planet is behind the sun. You can see a crescent Venus at eastern or western elongation. you can see a little more than that, but you can't see a half Venus because that's too close to the sun. You can't look, the sun may only be a half a degree across, but the brightness that blocks out things is several degrees across.
Yeah, yeah, right.
So, yeah. And even if you were to blot out the sun by using a coronal disk, what if it's behind the disk? You're still looking towards the sun and won't see it. So the best way to do it is get off angle from the sun and use radar at a frequency that is not being emitted by the sun. And now you can sweep the area and anything that's there will show up. Why don't we do that from Earth? Well, because when you get up to the 30 gigahertz range, the Earth's atmosphere tends to attenuate the microwave radio radiation. So you can't use a radar antenna from Earth to do this. You've got to have the radar source being out in space.
Yeah, yeah.
And well, why don't we just, put something in Earth orbit and do it that way?
Yeah.
Because you're still staring at the sun.
Yeah.
So yeah, L4, L5 are a better place to be doing this from. But putting things in solar orbit at L4 or L5 using new technologies like radar at 30 gigahertz that may be a couple of kilowatts of radar power, there's your $1 billion satellite plus launch vehicle. And yeah, it takes us, 10, 15 years to develop those things and get them practical and get them launched and operational. So when do you start looking?
Yeah, but we're pretty good at launching things to observe things.
Yes. Once we build them, once we decide to spend the money to build them, there was, I guess, between Carl Sagan and just some text in an episode of the $6 Million Man, if you remember that, where they said, if there's something targeting the Earth and you find out it's going to hit us, you've got a certain amount of time to plan for it. If there's something in the universe that's going to hit the Earth and you have no ability to detect it, when do you start looking for it? Well, as soon as possible. And when do you start developing the technology that will help you deter it from hitting the Earth? Or let's say it's gamma radiation. How do you defend the Earth from a gamma beam from a star that suddenly becomes a pulsar? We don't have the technology. We don't even have the physics for that yet. So when do you start studying how you would solve that problem? As soon as possible. And in the $6 Million Man, they made it akin to, if you're a student in school and you're going to be given a pop quiz and you don't know the subject and you don't know what it's going to take for you to learn the subject and you don't know whether or not you can come away with 100% A plus on the test results, when do you start studying and what do you start studying? Well, you study as soon as possible and you study everything. You become a polymath because you don't know what technology you're going to need to understand, what thing you're going to need to create, and how soon you're going to have to create it 100% successfully in order to defend the continued existence of life on this planet. Yeah, I don't think people are thinking in that terms. They're thinking of, hey, if we go find some big corporation and we toss $1 billion their way, they can create us something in the next 10 years that might stop something if we know it's going to hit us 20 years from now.
Yeah. And they could do it with different technologies,
right.
different departments.
What if it's going to hit us 5 years from now? Well, we'll give them $20 billion. I don't think math and physics works that way.
Yeah, that doesn't work.
So,
You can hear.
but it's October. Halloween's coming. Be afraid. Be very afraid. So,
yeah. Watch those witches. They come flying around on brooms. There's no way to deter them.
Yeah. We should start calling these asteroids the names of witches. Yeah. The next one of these we're going to call Gwendolyn.
There are a few famous witch names, aren't there?
Yeah. I don't think Wicked is one of them.
Wicked.
Yes.
Miss Gulch wasn't a witch, right?
Yes. I don't know. Samantha comes to mind.
Yeah.
But she was a good witch, sort of.
She was.
Okay. Any other comments or questions? I'll end it early tonight. Okay. Hearing nothing.
Okay, it's nice.
Thank you.
Nice to visit. We're in Joanne's car tonight.
Okay.